NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we'll learn a fast way to compare a real number p with the two real roots of a quadratic, without explicitly solving for the roots. The method uses the sign of a times f of p, and the vertex at minus b over 2a. Suppose f of x equals ax squared plus bx plus c, with discriminant greater than 0, so there are two distinct real roots, x1 less than x2. Our goal is to decide whether p lies between the roots or outside them, and if outside, on which side? Step 1. Compute f of p, and multiply by a. If a times f of p is negative, p is strictly between the two roots. If a times f of p is positive, then p lies outside the interval from x1 to x2. Step 2. If p is outside, compare p with the vertex x-coordinate, which is minus b over 2a. If p is greater than minus b over 2a, then p is to the right of both roots. If p is less than minus b over 2a, then p is to the left of both roots. For intuition, think about the parabola and its two real x-intercepts, x1 and x2, with the vertex right in the middle at the average of the roots. The sign of a times f of p tells you if p lands in the valley or hill between the roots or outside them. First, place p between x1 and x2. In that case, a times f of p is negative. Now slide p to the far right, beyond x2. Then a times f of p is positive. And since p is to the right of the vertex, p is greater than both roots. Finally, move p to the far left beyond x1. Again, a times f of p is positive. And now p is less than the vertex, so p is less than both roots. Example: let us practice on a concrete quadratic. Take f of x equals x squared minus 5x plus 6, where a equals 1, b equals negative 5, c equals 6. Its roots are 2 and 3, and the vertex is at x equals 2.5. Here is the graph. The blue curve is the parabola, the orange points are the roots at 2 and 3, and the dashed blue line marks the vertex at 2.5. Test 1. Let p equal 2.5. Compute f of 2.5, which is 2.5 squared minus 5 times 2.5 plus 6. That equals negative 0.25. So a times f of p is negative, and p is strictly between the roots. Test 2. Let p equal 4. Then f of 4 is 16 minus 20 plus 6, which is 2. So a times f of p is positive, meaning p is outside the roots. Compare p with the vertex at 2.5. Since 4 is greater than 2.5, p is to the right of both roots. Test 3. Let p equal 1. Then f of 1 is 1 minus 5 plus 6, which is 2. Again, a times f of p is positive, so p is outside the roots. Compare with the vertex at 2.5. Since 1 is less than 2.5, p is less than both roots. To summarize, if a times f of p is negative, then p lies between the roots. If a times f of p is positive, and p is greater than minus b over 2a, then p is greater than both roots. If a times f of p is positive, and p is less than minus b over 2a, then p is less than both roots. That is the complete method. Compute a times f of p to decide between or outside. If outside, compare p with the vertex at minus b over 2a to find which side. In this lesson, we will find the range of values of m so that the number 1 lies between the two real roots of the quadratic equation, mx squared minus 2x minus 1 equals 0. We will proceed in 3 clear steps. First, ensure two distinct real roots. Second, enforce the between the roots condition using the test a times f of k less than 0, and third, intersect the results. Step 1. Ensure the quadratic has two distinct real roots. The rule is the discriminant must be greater than 0, that is delta greater than 0, or b squared minus 4ac greater than 0. In our equation, a equals m, b equals negative 2, and c equals negative 1. Substituting gives 4 plus 4m is greater than 0. So m is greater than negative 1. We will call this set D1. Step 2. To place a number k between the roots of a quadratic, ax squared plus bx plus c, we use the test. A times f of k is less than 0. Here k equals 1. Evaluate f of 1, m minus 3. Then require m times quantity m minus 3 less than 0. That inequality is negative between the roots 0 and 3, giving the interval from 0 to 3. We will call this set D2. Step 3. The final valid values of m are the intersection of the two sets. Intersect D1, m greater than -1, with D2, the open interval from 0 to 3. The intersection is the open interval from 0 to 3. In this lesson, we will compare two numbers with the roots of a quadratic equation, using sign logic that works for any parabola. First, let f of x equal ax squared plus bx plus c, with a not 0. Suppose it has two real roots, x sub 1 less than x sub 2. We'll draw a representative parabola opening upward to visualize the signs. We mark the roots at x equals 1 and x equals 3 for this picture, with the vertex at x equals 2. Case 1. If a f of p is greater than 0 and a f of q is less than 0, then p lies outside the roots and q lies between the roots. In symbols, p less than x sub 1 less than q less than x sub 2. Case 2. If a f of p is less than 0 and a f of q is greater than 0, then p lies between the roots and q lies outside. Symbolically, x sub 1 less than p less than x sub 2 less than q. Important note, exactly one root of f of x equals 0 lies between p and q if, and only if f of p times f of q is less than 0. Because a squared is positive, multiplying both sides by a squared does not change the inequality. Case 3. If a f of p is less than 0 and a f of q is less than 0, then both p and q lie between the roots. So x sub 1 less than p less than q less than x sub 2. Case 4. If a f of p is greater than 0 and a f of q is greater than 0, then both p and q lie outside the interval of the roots. We compare with the vertex, x equals negative b over 2a. If q is to the left of the vertex, then p less than q less than x sub 1 less than x sub 2. If p is to the right of the vertex, then x sub 1 less than x sub 2 less than p less than q. If p is left of the vertex and q is right of the vertex, then p less than x sub 1 less than x sub 2 less than q. Let us verify with an example. Example: f of x equals x squared minus 4x plus 3 equals 0, p equals 0, q equals 2. The roots are x sub 1 equals 1 and x sub 2 equals 3. Evaluate a f of p and a f of q with it equals 1. On our diagram, p equals 0 lies outside the roots where the function is positive, and q equals 2 lies between the roots where the function is negative. In this example, we will find all real values of m such that exactly one root of the quadratic equation x squared minus, open parenthesis, m minus 1, close parenthesis, x plus 2 equals 0, lies strictly between -1 and 2. We'll follow a 5-step algorithm. Define the function and interval, state the sign change rule, evaluate at the endpoints, solve the resulting inequality, and read the final m intervals. Step 1. Define the function and the interval endpoints. Let f of x equal x squared minus, open parenthesis, m minus 1, close parenthesis, x plus 2. The interval endpoints are p equals -1 and q equals 2. Step 2. Use the sign change rule for exactly one real root in an open interval. Because f is continuous on the real line, exactly one root lies between p and q if, and only if f of p times f of q is less than 0. For this quadratic, equals 1, so we simply require f of -1 times f of 2 less than 0. Step 3. Compute the endpoint values. F of -1 equals -1 squared minus, open parenthesis, m minus 1, close parenthesis times -1 plus 2, which simplifies to m plus 2. F of 2 equals 2 squared minus 2 times, open parenthesis, m minus 1, close parenthesis plus 2, which simplifies to 8 minus 2m. So the product condition becomes, open parenthesis, m plus 2, close parenthesis, times, open parenthesis, 8 minus 2m, close parenthesis, is less than 0. Step 4. Solve the inequality. First, find the critical m values by setting each factor to 0. m plus 2 equals 0 gives m equals -2. 8 minus 2m equals 0 gives m equals 4. The product, open parenthesis, m plus 2, close parenthesis times, open parenthesis, 8 minus 2m, close parenthesis, is a downward opening quadratic in M, so it is less than 0 outside the roots. Therefore, M is in the union of the intervals -∞ to -2, union 4 to infinity. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.